All right, hi everyone. So I'm going to be talking about IPVM, fearless execution for the open world. So I figured I've given a bunch of talks at these things about like the basics of what IPVM is, how it differs from Filecoin or other systems, and so I threw this together last night. We were at the drinks. I was like, I'm not giving a talk. I'm like, do you want to give a talk? I'm like, well, I guess I can. So I aimed this to be about 15 minutes, but I'm not actually 100% certain. And it's mostly like meant to give a very high-level overview of sort of the goals, and then it then jumps a few layers down, not like into the code, but sort of some of the parts that people may find interesting for other projects that I've had a few questions about, like fault oblivious execution or WIT IPLD and a few pieces like that. So Joe Armstrong, the guy behind Erlang, in the last years of his life, he passed away a couple years ago, had this idea that, what if we could have every process in the world talk to every other process? So kind of like TCP/IP for machines, but at the process layer. And Microsoft Research and the Azure team have this idea of fault oblivious execution that says, well, as long as we can keep things down to pure data processing, so things that we can, in fact, hash, then we can isolate all of the failure away from developers and make distributed computing significantly easier using all the things that we've learned in the past 50 years of databases, but applied to general compute. So basically mashing those two ideas together is the underlying underpinnings of IPVM. I'm Brooke. I think most people here know me at this point. I'm the co-founder and CTO at Fission. And the other person on this slide, this is Zelenka. He's been leading the Homestar implementation of IPVM at Fission. So we always wanted to get to compute at Fission. So we started in 2019. And we were like, we're going to do a compute platform. And to do that, we need distributed data, which is how we got involved in IPFS. But then we realized, well, there's no encryption story, and there's no really robust CRDTs, and encrypted CRDTs are a whole thing. And so we needed to build out that data layer, and in order to do that, we needed an auth layer. So we did UCAN at the bottom, web native file system, and Rhizome in the middle, and then now we're just getting to IPVM now. Unlike the 90s, when the web was being invented, we now have a very heterogeneous network, right? And blockchains, for the most part, focus on living in their own world, right? We need to have consensus, therefore we need to restrict what's around the world. But in the real world, things need to spread across lots of different things, right? We have very powerful phones. The processors in laptops are very, very powerful now. You can do a lot of compute locally, but you also need to talk to the cloud and edge and to things in Commons networks, right? IPFS, BitTorrent, Ethereum, et cetera, right? And you need to spread across all of these. We also want to be able to compose apps together arbitrarily, right? So I don't want to have to write custom code to call into Ethereum or into Filecoin. I want it to just kind of like have a single interface and just have it taken care of, right? With UCAN and capabilities generally, which we're not going to get into too deeply here, there's a single interface, and mediated with crypto, you're able to now, without pre-negotiation, without having to do a bunch of work in advance, tie together services, which is really important for some of the stuff we'll talk later in about IPVM. So really what we're talking about at, again, the 10,000-foot view is connecting every service in the world with all of the users without pre-negotiation. One way of thinking about this is trying to build an HTTP for compute, okay? Open, interoperable everywhere, runs locally, runs under network partition, doesn't require consensus. And if you have connection to other services, then it just gets more powerful. And all of this has to be substantially better than the status quo, right? We actually have to compete with Cloudflare workers and AWS Lambda, right? It's not saying well, it's like these things, but you trade these other things off to get distribution. It has to actually be substantially better for Web 2 users as well. So trying to take all of these silos that we've built and tie them together. There's an old idea in distributed systems called disorderly programming, where you don't have to make everything perfectly clean and aligned ahead of time, where you can just sort of grab a bunch of stuff and tie them together and try things out. And if they don't work, that's fine. You can roll back and keep going. But like, how do you roll back when you don't have full control over the entire system, right? Where you're grabbing these separate things. And that's a big part of the underlying bits of what IPVM does. The other thing is, historically, you need to have these very, very high availability systems, which arguably blockchains are, right? The people at AWS, super brilliant engineers working to get very high number of nines of reliability. But the way that they do that is they take things that have lower reliability, put them behind an abstraction, and now you have failover, right? That's literally how everybody gets, 9 nines of reliability. So if anybody can become a service provider, then the network itself has very high reliability. It has, arguably infinite nines, especially for things that everybody can run, like WebAssembly. So at the base layer, IPVM runs WebAssembly. Everybody can run it. You can run it in your browser. You can run on a server and everything in between. And everybody else on the network also runs it. So if you're online, you have, assuming people actually run the Homestar node, you have lots of options very close to you to run this. Fundamentally, I think developers don't want to be made to think about where they're going to run things and how they're going to run them. One of the big advantages on a blockchain is that you just submit it to someone, and then the whole network knows how to handle that, and it's abstracted away from you. The hard part here is if you're in a world where things can change, how do you make that safe, right? So I just want to be able to dip down into the underlying compute substrate of the world and say, okay, cool, here's a bit of compute. And for pure computation, that's very easy, works today. How do you get that to work with email and HTTP requests and all of these other things? So let's talk about this magical compute substrate. As I said before, we needed auth data and compute, and those need to run everywhere. So we can't use a centralized OAuth server, right? So we invented UCAN. So UCAN at the bottom, web native file system, which is built on top of IPFS with encryption and concurrency and multi-writer and all of these things in the middle, and Homestar now as our compute node on top of that. And so altogether, this whole stack gets exercised with IPVM. The really core idea for the execution model is that code is data. And so we can take our WebAssembly module, content address it, and now it's just another bit of data like anything else. So those of you who were in Steb's talk yesterday about FVM, this is essentially the same idea, right? Instead of having code, long-running code that sits somewhere, and you say, hey, call into that thing, the long-running bit of code that has some state and it's an object. You say, no, you can load arbitrary arguments into arbitrary WebAssembly and run them basically, as long as you can get them onto the same machine. They don't even have to have started there. You just pull them into the same place and they can execute. The way we do this is by obviously hash linking them. So this is all IPLD. Under the hood, we give it a little bit of hints with scheduling configuration. So maybe this needs to have a timeout or a gas limit, things like that. And then the task gets a unique task ID. That's not unique for now, it's unique for all time. So if you have something that is impure, we'll talk about that in a little bit, then you have to apply a nonce. Otherwise, if I run this now, or in a week, or in 10 years, or you do it, you will get the same result. Because WebAssembly, if you enable canonical floating points, is a deterministic execution runtime. One way of thinking about this task is like having a closure in any language, like in JavaScript. So when you have an alert, if you wrap a function around it, it's not going to execute right away. You can pass that reference around to anybody, and that's totally fine. Nothing's going to happen. You have to actually apply the braces to it, the parentheses, for it to actually do that. So the equivalent of those parentheses for us is a UCAN invocation. So you get a signature and an actual agreement that it'll get run. On the other side, you get back receipts, which points at the original task, and then any values and effects. We're going to spend a lot of time today talking about effects, and a little bit of trace data. So basically, I asked it to do 1 + 1, it gave me back 2, and it's wanted me to schedule some more stuff, right, is the effects part. Here's what that actually looks like. So the format has more things, but this is concretely what this looks like. So you have a URI. You'll notice that has the IPFS prefix on it because this can be any URI. This could be a HTTP or a mail to or literally anything. We try very hard to bake things down into hashes whenever possible. We then say call on that. Well, I'm going to treat this like WASM. This isn't Docker. This is a WASM thing. So treat this like WASM run. And here's my inputs. The function on this module is add1, and the argument is 42. But what if I don't know what the argument is yet? I have some other process that's running, and I'm waiting for it to finish. Well, I don't want to have to wait for that to send me a result back, and then for me to spark the next step. So we just say, hey, here's a promise. Await on the OK branch. And here's the hash of that other task that we're waiting on. And so as soon as I see a receipt for this, I can use that. And this has some actually really nice downstream benefits, which, for example, if I got halfway through a workflow and it fails, well, I still have all of these around. And so I can skip all of the previous steps because I have the receipts. I don't have to run them again. So this means that we, instead of having to always know where the data is located and where the compute can happen and having it run on like a particular EC2 instance, everything's addressed by this input ID, by these tasks, and we tie things together in workflows as a directed acyclic graph, right, using data flow and awaits. And so this is a really natural programming model for normie developers who know about async await in JavaScript, right? It looks the same. You don't even have to give us the tasks in a particular order. You just hand them as an array, and the scheduler handles the tying together of them and figuring out what needs to come before what. And programmers can't screw up having loops and things because there's hashes, right? It has to go in one order and has to terminate. The scheduler then can make really smart decisions about this because we're not saying run this here, run that there. It's at a higher level, right? And so this is the same as this, just broken up on 2 separate machines. And saying, well, maybe, Alice and Bob here. Alice has a bunch of the data I need to compute over for these 2 steps, and Bob has these other 2. Even though it is this diamond shape, the scheduler is able to figure this out. Finding where the resources live is like the hard part. Actually doing this part of the scheduling is trivial. Again, the default thing that we run is WebAssembly. You can run sort of arbitrary calls, and we output these receipts, IPLD receipts, at every step, but that has an overhead. So we actually combine them together using the WebAssembly component model, and then asynchronously tap out the binary that gets returned, and then convert those into these receipts that we need. The receipts, again, because it's deterministic, means that if somebody else had the same first few steps of a workflow, they don't ever have to run those again. We just skip those and continue execution from that point. This is based on PDFs, and I only have so much time to talk, but the demo we usually give for this is we crash the node halfway through and restart it, and you pick up right where you left off, as long as you can get those receipts. Or you can start another node on a totally different machine that's never seen this stuff before. As long as those 2 can talk to each other, it can pull those receipts out and skip all of these steps as well. With IPLD, a bunch of people have been asking about this recently. The interface for IPVM is all in IPLD schema because WIT is a pretty low-level format, A, and B, it's changing all the time, and it kind of is a pain right now. So we're doing all of the fixing and abstraction under the hood for that. So that's WITs, which is the WebAssembly interface types from the component model. They like to give you a sense of how often this is changing. It changed on us last week, 3 days before I gave a talk about it. So making these updates isn't hard. It's just, it's not settled yet, right? So those are two that aren't even in a lot of the documentation. So they don't have like, well, Enum's been around for a while, but they have records. And actually, this is a bit of a lie about IPLD schema because we also have some extra stuff here. And there's an impedance mismatch between these, right? They don't map directly onto each other one-to-one. Like a bunch of these things are in there, right? And you can just say, when I get one of these, treat it like one of those, and that's not a problem. Harder is that some of these map one way and not the other, right? So IPLD schema doesn't have sizes for signed and unsigned integers, for example. So we treat everything today as 64-bit, for example. We don't have a char type. Links, there isn't really a good link type in WIT, right? So there's a little bit of inference that we have to do along the way. Handles are actually kind of an interesting one because we do use those inside of IPVM. This is getting a reference to something outside of the module. We actually use that, but we don't want it to have a serialized representation, right? We do things like, so we call this a content handle as opposed to a content address. You give us a CID, and we find out who has that data. So it's a petabyte of data somewhere. They're going to guarantee to us that they have that. We convert that under the hood into this handle type, and that lives as a witness that somebody, this particular node told us that they had the data. So if we fail halfway through because we can't load blocks, we know who to blame. Verifiable computation. So it's in a flexible model. You don't have to verify things, but by default, we use optimistic verification. So essentially, you check, hey, do you agree on the last one? No? Okay. And then we do a split search, a binary search on the previous receipts to figure out where we disagreed, and then send that to an arbiter and slash them economically. So there's an incentive to not lie to the network. We think ZKPs are going to be really important for this, and there's been a bunch of work in doing WebAssembly on top of zero knowledge. It's not quite there in terms of speed today. Like you definitely trade off performance, but it's something that we want to do in the future. All of this determinism also means that you essentially get a reverse lookup table. So if you're going to, let's say, do moderation and tagging on AI data, you've looked at a video and to check, like, does this hit community standards, et cetera. As soon as one person's run that, and it's verified and trusted, or you have enough receipts that you trust it, you don't have to run that again, right? You can skip that computation, or you can say, hey, does anybody have a thumbnail or a cropped version of this image? We get that essentially as a global memoization cache for everybody in the network. Safety comes up a fair bit with this stuff, and then this is the last section, then we can get to questions. So we talk about matchmaking. The system doesn't, we're going to have some built-in things, HTTP, DNS, email, crypto, random numbers, things like that. But let's say that you have something that we don't bake into the system, right? Like, let's say you run a fish-themed Docker network, for example. Somebody can put their hand up and say, hey, I can run Docker containers. Oh, I would like a Docker container run. And the network itself doesn't care. It just knows how to do that routing. Or maybe you come up with a, totally new format that uses GPUs. They can say, hey, I have a GPU. Oh, cool, great. And they'll just route that around. For all of this stuff to work, we have to separate out the pure computation from effects, so things that go out into the world and make changes. People are usually, I think at this point, pretty familiar with the concept of a side effect, a thing that runs mid-computation, right? So 1 + 1 = 2, and then make an HTTP request and then continue. We actually have to break those into separate components for the network to know how to handle things safely, right? If something's totally deterministic and pure, we can be really loose with how we schedule that. And if the effects are separate, then we can actually even move them around in the execution order as well. So if you have something that is just pure computation or a query, so that's an HTTP read or create a random number or decrypt some data, all of these things, it's actually totally safe, and you can rerun them and you can roll back, right? You can be very, very loose with how those work. When you need something with exact once execution semantics, so I'm going to send, post something to Blue Sky. Well, I don't want retries to interfere with that, so I need to get a lock on the process, run it, and then write back, hey, I ran this thing, I swear, and then unlock that, right? The performance of this, interestingly, is that ends up looking like how somebody would run something in AWS. And everything to the left of that can be scheduled with way lower latency and with what we call fault oblivious execution, i.e. it can be retried infinitely. We can skip steps in the execution, like all of that nice stuff. So the three properties we care about are mutability, idempotence, and determinism. And we can interleave queries and pure computation as much as we like, as long as mutation is kept to the bottom, right? And so this is the stuff from off the top when I was saying Microsoft research has done a bunch of stuff on fault oblivious execution. They have a number of papers on it. They've actually done this inside of Azure as well for their durable functions. Works really nicely. It has this one caveat. You can't interleave mutations, because as soon as you do this, if you fail halfway through, now you need to know how to roll back that mutation, right? And you can't roll back all mutations. Some you can, some you can't. So this query versus computation thing is a simplification. It's those three properties, mutability, idempotence, and determinism. The combination of those lets us know how safe a particular part of the execution is. So this is the simplified view. Queries and computation go back and forth. As long as you end, any mutation that happens is at the very end. And that also means, because we have this DAG execution, the only guarantee we've given to the user is that the data will flow. We're not saying that it'll happen in a particular sequence. So if we have something that's shaped like this, we can push the mutation to the end for them. So there's a little bit of analysis that the machine does in advance. Because it's a DAG, we don't have loops, but you can still do loops in the system. Because the end, when you get back your value, you also get anything else you want to on-queue. And so we can use recursion to do this by scheduling the next of those steps. Here's all the specs we've written for this. There's a bunch of work going into this still, especially UCAN channels for payments and other consumable resources. Workflow and tasks need some updating versus where we've actually gotten to. So the text should be getting updated shortly here. If you don't like a part of this, you can swap out another bit that you're using. Or, if let's say you really like invocations and you want to put those, embed those in the DHT or something, which apparently something people are doing now, there are useful things in here outside of IPVM. Take them, reapply them, get involved. They're all in working groups. So those two there, UCAN working group and IPVM working group. Thanks. I think we still have time for questions. Yeah, great.
Perfect. All right. Thank you.
Okay, I kick it off. So I'm curious because you mentioned that you're using IPLD under the hood and schemas. Mm-hmm. Is there, can you share the implementation? What because I guess this is Rust the last time I saw it. Mm-hmm. So you have a schema Rust IPLD implementation? And below with, that would be really interesting.
So it's on the outside, and then we convert it into WIT. And then the actual execution is all in WIT until we get to the end when we convert it back.
Right. So you have you exchange IPLD schema serialization, you do WIT inside WASM, mm-hmm. and then when you persist it, you get, you persist it as IPLD schema.
Yeah.
Also. Okay.
Yeah.
Understood. And the second question that I had is what, so because I have IPVM, I want to build an app. Is there if I'm a developer, what would be my developer experience? So is there a programming language, or like I need to build so what is the state? I'm curious about what is the state. Like I need to build the WAS module, deploy it, and then like do the hooking between the different modules.
Yeah, so you need to build the WASM module, and as long as you can get so we're still relatively early, right? We've only been coding like actual fingers on keyboard with this since February or so. So it's like relatively early still, right? It runs, it works, but the developer experience needs help still, right? There's a few manual steps right now. You compile to WASM, you get a CID back, and then those get fed into UCAN Invocations and then wrapped in a workflow. So there's no special programming language for this. You can write in anything as long as it supports WebAssembly components, which today is not a ton, right? Because the component model is still changing, right? So C, C++, Rust, Python all work. Surprisingly, JavaScript, there's a shim for it. There was one for when it was still the WASI project, but things have changed so much that they've kind of just left that until it finishes, right? We're getting to know the folks at WebAssembly Component like working group, and they're like, end of this year, maybe early next year kind of thing, so we'll see. As long as you have CIDs for the modules, the system knows how to pick up the rest. So all of the tooling today is, like we're working on essentially, everything right now is essentially working in the IR. The tooling on top of that is going to be integrating into a bunch of different languages to be like, hey, I'm writing in whatever, Rust. Here's the code I want you to execute as a transaction. So here's my transaction block. And so there'll be like language-specific DSLs. As well as, we've been experimenting a little bit with web UIs as well. I'm not sure if people here have seen Valtown, but it's almost like a runnable gist with like a little play button in the corner. Same thing. I should be able to write code like in the browser and just try stuff out, right? And have that talk to the network. So we're playing around with a couple different approaches.
And for the infrastructure, what are you envisioning? Because like I see two dimensions here, right? The operation experience and the developer experience.
You run a Homestar node, and you're done.
Okay.
So part of the grant that we got, we need to integrate this into at least one IPFS node. So the experience will be, depending on like, the exact archetype, IPFS run this WASM module, these arguments, and it'll run for you. That's for like IPFS developers. For people that just want to run this on the network, you spin up a Homestar node. By default, that has WebAssembly baked in, and then we don't have these today. Hopefully, in the next sort of like few weeks slash single-digit months, HTTP, DNS, crypto, random numbers, like a few of them out of the box. Anything else? So let's say you want to run plug-in CUDA jobs for GPU. Using WebAssembly components and with a standardized interface, you can drop those into a directory, and that's a plug-in system. And so as long as you can understand the message type, the system will route automatically and be like, oh, they said that they can do that for you. And it then the Homestar node knows how to use that plugin.
Yeah, I actually have a continuation of this question.
Yeah.
The Homestar nodes or whatever other execution environment that you prefer, right? I understand this can run pretty much anywhere, but several times you said the network talks to the network, advertises to the network. In your view, in the ideal case, what is the network? Is it kind of like an IPFS swarm with a DHT kind of thing, or it's more like a Filecoin thing? What is it?
Yeah, so you could put some of this stuff on a blockchain as well, right? Similar to the LilyPad. That is not our focus today, right? Under the hood, we use libp2p and pubsub with that. We're also planning to run IRO network under the hood as well, so we'll have both. We publish receipts to a DHT that's specific to this network. If and when the DHT generalization proposal goes through for the main network, we would probably switch to that. But it's not like today we just use libp2p under the hood.
libp2p with your own DHT swarm.
Yes.
Okay, thank you.
Yeah, and most things, like for speed reasons, go over pub/sub and then direct links whenever possible. Step.
Thank you. Sorry, questions. Okay, so like you're calling to specific WASM functions here, but is there any way to like isolate these WASM functions? Because like, how to put this? My concern is like, if my compiled WASM binary is slightly different from yours, the addresses are going to be different. Is there any way to like minimize that and like maybe like turn it into some structural thing that like probably converges?
That would be nice. We're not worrying about that today. We think actually, like, there is this ad hoc execution model, right? So like, it would be nice to just do single functions at a time. We think most people won't write, except for glue code, won't write the majority of things. There will be a task registry, and people will say like, oh, I want to tie it together almost like an NPM, right? And tie those things together. Yeah.
Okay, that makes sense. Thank you. Then I guess the next one is why like data receipts instead of codes? Like you have like JSON receipts here, but like at least usually when I'm trying to write some code, like I write some code that spawns another task and then it pulls in the result and sort of goes back and forth. But here I see like you sort of build this tree where you say like explicitly like JSON object await this thing. I'm wondering if you like what trade-offs you considered there, especially because like there are many cases where like I may depend on one of two tasks, but I won't know which task I depend on until I run a third task.
Yeah. So that dependency, like that not knowing, has to get baked into the tree, basically, and then you can throw one of the values away, right? We're taking away a lot of control from the programmer because we don't want them to have to learn all of distributed systems.
Yeah, my concern here is that means basically like, in this case, I need to run both computations even if I don't know which one I'll need, instead of being able to basically say, okay, I know I need this one computation. Let's me decide which of the other two computations I need. And then I just like, does that make sense? Where like effectively, like here you have this very simple or straightforward tree of like JSON objects.
Yeah.
Where like instead of what I would almost like is more like, okay, I have one program that doesn't necessarily depend on anything yet, and then it effectively emits. This is like the effect system where you emit an event or you emit an effect or something like that. But this is not actually an effect; just like it's emitting a dependency and then waiting on that.
Yeah. So you mean branches, basically?
Branches, yeah. But it's like but it's like also how like coroutines work usually and stuff like that, where like or async await, where you basically say, okay, I want to wait on this thing, but you do this programmatically instead of just like hard coding it.
Yeah. So for branches, again, we describe that in advance in the same way that in async await you're describing that in advance, right? And you say, I'm going to await on some code, and then I'm not going to feed this one side. I'm going to feed that other side, right? It's data flow, right? So that works. If you want to do anything that's fancier than that, like during the execution, I decide that I want to load new WASM, this instead of that, then you use the effect system and you take the performance penalty. Yeah.
No, but my question is, sorry.
I don't know. Does it go in the direction of not speculative execution and stuff like that? That sounds pretty much what CPUs are doing, what you are doing in the end. Is it possible to execute not yet specified branch of your tree?
So it will run, like, it'll run anything that it has arguments for, right? So if it has all of the arguments and they're, as raw values, it will start to run those as soon as, all other things being equal, it'll start to try to execute those in parallel immediately, right? When you have a data dependency, so you're saying, I'm waiting on this thing to finish, and when that value's done, pipe it in here, it can't speculatively execute because it doesn't have the data for it yet. So it's more like graph reduction than a sequence of steps.
It's very much like Spark. But final question on handles. So you talked about using handles and links and stuff like that. Do you actually use handles to represent IPLD links, like when you decode, or how does that work?
So handles don't represent IPLD links. They represent a pointer to something that is not a value that's already in the system.
Okay, I'm just wondering like how it's like. Okay, never mind. We can talk about it later.
Okay, yeah. But they basically point to the top of a data structure. And then there's a block store that the interface is, give me the next block, give me the next block.
Okay.
Right, yeah.
Thank you.
All right, fantastic. We are over time. Thank you
Sorry.
so much. Thank you for the great questions. I mean, so yeah.